Hey there, welcome back to our course Advanced Quantum Mechanics. This is lecture 26. Remember that predictions are calculated usually this way. Predictions F bar is equal to psi F hat psi. Now, this assumes that we know the state of the system. Now, if we do know what the state of the system is, then we say that the system is in a pure state. So here's the definition. If we know the state psi of the system, then we say the system is in a pure state. Now, on the other hand, in practice, we often don't know what the state of the system is. And if we don't, then we say, else we say that the system is in a mixed state. In a mixed state. Now, why the word mixed? Well, the reason why we say mixed is that the uncertainty in the predictions then arises for, then have mixed origins. So, why mixed? Why would we use that word? It's because the uncertainties of predictions then have two origins. They are of mixed origin. Namely, on one hand, there is the usual quantum uncertainty, what follows from the uncertainty principle, and just generally because states are not necessarily eigenstates of the observable that we want to measure. So there is quantum uncertainty. But then there's also uncertainty in the outcome of a measurement because of the ignorance of the state. Because we don't know what state the system is in. Now, when the system is in a mixed state, it doesn't necessarily mean that we have no idea what state the system really is in. Often we can assign probabilities to the state that the system might, to the states that the system might be in. So often we can assign probabilities. To the states that the system might be in. And towards the end of this lecture today, we will try to quantify how well we know the state of the system. It can go all the way from I have absolutely no idea what the state of the system might be to I'm sure I know what the state is. So that's a question that we will come to at the end of the lecture, and we will answer it information theoretically. So there are two main cases for when we can assign probabilities. Two main cases that are such that we can assign probabilities. The first case, oh, what happened here? So the first case is system was in contact with a heat bath. Now that sounds fancy, but this is absolutely the norm. An atom is always exposed to the temperature of its environment. Every quantum system, if we don't take special precaution, is exposed to the temperature of its environment. And many times the environment is fulfilling the conditions of a heat bath, meaning that it has a well-defined temperature and that it is big compared to the system that we are bringing in contact with it. So when the system was in contact with a heat bath, then the system has been exposed to random kicks due to the thermal activity in the heat bath. So for example, an atom in a heat bath, for example, we might have an atom in a gas, and the gas has a certain temperature, then our atom gets kicked around all the time. And sometimes it gains energy from a kick, sometimes it loses energy from a kick. And the hotter the gas is in which our atom is, the more violent are the kicks. Now, what should we expect here? Well, what we should expect for our atom in a heat bath, or generally for any quantum system in a heat bath, is that the quantum system that's exposed to the heat bath could be found in any state, but the higher the state is, the higher the state that we consider is in energy, the less likely it is we find the system in that state. The system is more likely to be found in lower energetic states than to be found in higher energetic states. However, if we crank up the temperature of our heat bath, then we expect that, yeah, even the higher energetic states become slowly more and more likely. We will calculate the exact distribution as a function of the energy, as a function of the temperature. We will calculate the exact probability distribution on information theoretic grounds later in this course. So this is one example where we can do this. When a quantum system is in contact with its environment, and the environment has a certain definite temperature, and the environment is big compared to our system, meaning that the environment doesn't get cooled down by our system or heated up by our system, well, then it is possible to calculate exactly what the probability distribution is for our quantum system to be in the various states that it could be in. The second possibility, the second scenario, the second situation where we can calculate the probabilities for the various states that our system might be in is right after a measurement. Right after a measurement. Actually, right after a complete measurement. Remember what that means? It means that either we measured an observable whose spectrum was non-degenerate, meaning that every eigenvalue has just exactly one eigenvector associated with it. And that means that if we measure an eigenvalue, we know exactly what state the system is in afterwards. If we are measuring an observable that has degeneracies in its eigenvalues, well, then we can measure more observables at the same time that commute with the first observable, such that eventually, once we've measured all of those commuting observables, we know exactly the one-dimensional space in the Hilbert space in which our system is after we've measured it. So let's say we measure, for simplicity, an observable whose spectrum is non-degenerate. Then after that, the system is going to be in a new state. The wave function collapses. but it could be in any one of the possible eigenstates of our observable. And we calculated previously what the probabilities are that a incoming state collapses into the various possible eigenstates of our observable. This means that we can calculate exactly what the probability distribution is of the various states that the system might have collapsed into right after the measurement. So we have a probability distribution of what states the system might be in there. Now, of course, if we read the output of the measurement instrument, then that will be the eigenvalue that was measured of the observable, and therefore this probability distribution, this uncertainty, collapses into a certainty, because we know, aha, this eigenvalue was measured, therefore the system is in this state. But imagine we are looking at an ensemble of measurements. So we have an ensemble of experimental runs. Then we get the probability distribution for the outcomes. And that's important, because imagine we want to calculate, to predict what will happen in an ensemble of experimental runs, where the system evolves, then this measurement of the observable takes place, wave function collapse takes place, and no matter what the outcome is of the measurement, we are going to let the system continue to evolve. In this case, there's a probability that the state collapsed into one eigenstate of the observable and then continue to evolve from there, but it might also have collapsed into another eigenstate of the observable and then continue to evolve from there, and it might have collapsed indeed into any eigenstate of the observable and then continued from there. This is a mixed state situation right after the measurement if we want to keep describing the entire ensemble. As you can imagine, this can get a little tedious if we are not doing good bookkeeping, because what it means is that when a system is in a mixed state, for whatever reason, either because we've just performed a measurement and we're looking at the entire ensemble there, or maybe because our system has been in contact with a heat bath, or for whatever reason, we lost track of what state the system is in, and we can only assign probabilities to what states it might be in. In that case, in order to track the evolution, we have to track the evolution of every state that the system could possibly be in. And in order to do this bookkeeping efficiently during the dynamics, a mathematical tool has been invented that is very useful. And that tool is called the density operator. So let's assume, that, okay, yeah. Assume that we have a Hilbert basis of our Hilbert space, and assume that the probabilities are known for the system to be in any one of these states. Assume known the probability for each of these states. And let's call these numbers rho n. So rho n is a number between 0 and 1. Each rho n is the probability that the system is actually in the state Bn, unbeknownst to us, but well, at least we know the probabilities. Now, in this case, what do we know? Well, we know that the sum of all the rho n has to be 1, because the system is in some state. And what are now the predictions? Remember that we had that the prediction of an observable is the sum over n of rho n. Sorry, I was dashing ahead here. Is psi. Sorry, it was my thoughts already with the next argument here. F hat psi, right? This is what we used to have. Now we have that the state is not psi, but the state is any one of those states Bn with probability rho n. So what value are we going to get for as expectation value? Well, this is for pure states. Now, what we are now going to get is that this is the sum over all n, and then the probability with which the system is in state, Bn, and then the expectation value of our observable in the nth state. Right? So this would be the expectation value of f if the system is in the state Bn. And now we have the weighted average of all those, weighted by the probability that this is the state of the system. Okay, let's give this equation a number. Let's call it red star. Now, we define the so-called density operator using these quantities. So, definition. The density operator is defined as this operator. Rho hat is the sum over all n, and then these probabilities, and Bn. Let's look at this operator. Is it an operator? Sure, it's an operator, because it's going to map vectors into vectors, right? It's just like a sum of projection operators, actually. It's a weighted sum of projection operators. But also, since the Bn, by assumption, are a Hilbert basis, we see that this operator is diagonal in the Bn basis. We see rho hat is diagonal in the Bn basis, right? Because if we look at this, Ba, B, then what it's going to be is rho A delta A B, right? Because we have all these Kronecker deltas here. So rho hat is diagonal in the Bn basis, and all the rho n are real. In fact, they're between 0 and 1. What we can tell from this is that rho hat is a self-adjoint operator. However, keep in mind, it's not an observable because it describes the state. It's the only operator that describes the states, whereas all the other operators could be, all the other self-adjoint operators could be observables. Okay, so rho hat is a self-adjoint operator. It's a density operator. It's also called density matrix. Also called density matrix. With the understanding that it's an infinite by infinite matrix. Now, conversely, Conversely, consider a self-adjoint operator that has these properties with discrete spectrum, where all the eigenvalues spec of rho hat are in the interval from 0 to 1, and we have that the rho n, sum over rho n, equal to 1, so that, you know, they can represent a probability distribution, namely the sum of all probabilities has to be 1. Well, then such a rho hat can always be viewed as a density operator. And why is that? Well, it's because if the operator rho hat is self-adjoint, well, then in its eigenbasis, because in eigenbasis of rho hat, we have that rho hat is diagonal, and it's going to be sum over n, eigenvalues rho n, and then we have, yeah, let's call them rho n eigenvectors, why not? They used to be called the Bn. But in any case, what we see is that these guys then are positive, they are between 0 and 1, they sum up to 1. So in other words, every such operator can serve as a density matrix. Now, how do we make predictions now? Remember that in the case where the state was pure of the system, that is to say, in the case where we know what the state of the system is, namely psi, this is the method for calculating expectation values. In the case where the system is mixed and we have a probability distribution for what state the system might be in, then the expectation values are calculated in this way. So now, once we have the density operator, how can we express using the density operator how predictions can be made? Here's a proposition. F bar predictions can now be calculated as the trace of the density matrix times the observable. And before we prove that, let us notice something. This is, because it's a trace, this is basis independent. As it should be. Should be. Right? Because this is an actual prediction here, the F bar. It's something measurable. And of course, something measurable cannot depend on a human-made choice of bases in a Hilbert space. And neither does this trace, because the trace of any operator is independent of the basis in which you calculate it, which is a cool result of linear algebra, if you think about it, because the trace is simply the sum of all diagonal elements of your matrix. And if you change bases, then the diagonal elements change, but their sum doesn't change. The trace is basis independent. So now we have to show, prove that trace of rho hat f hat is actually equal to what we had up here, namely that it's the arithmetic mean of the predictions for each one of the individual states. And that was here, right? This is for the pure state, this is for the mixed state. So we have to show that it is this expression here. So that it is equal to the sum over rho n bn f hat bn, where these guys are the eigenbases of rho hat. So this is what we need to show. Okay, let's prove this. Let's start with the trace of rho hat f hat. Well, it's a trace. So we can write it as the sum over n, and then we choose the basis, and we choose the eigenbasis of the rho hat. So let's write it as sum over the bn. We could also call them rho n. I'm hesitant. It doesn't matter. As long as we keep in mind that the bn are the eigenbases of the rho hat operator. And then here we have bn. So this is literally just calculating the trace. Here we have an operator, and the trace of it is the sum of the diagonal elements. Here we go. That's the trace. Now, what is rho hat again? Remember what rho hat was. Let me show you. We define rho hat in this way. Right? In its eigenbasis, it is simply the probabilities multiplying the eigenvectors here. All right, so let's write this out. So this is then the sum over n bn, and then I'm writing out what the rho hat is. This is the sum over m rho m bm bm and f hat bn, right? Okay, so we can pull this sum and this number in front. So this is then the sum over n and m and rho m. And then we have bn, bm, bm, f hat bn. And this then is, because this is a Kronecker delta of n and m, one of the sums goes away, let's say the m sum, where m has to be equal to n. So we are then getting the sum over n, rho n, bn, f hat bn. But this is, by the equation with the red star, this is equal to f bar. So we're done. So this was the weighted average over the predictions for each one of the states. Now, pure states are special cases of mixed states, simply where the probability distribution is super skewed, where all the probability is on one state. And so for this particular one state, the probability is 1 and all the other states have 0. So let's ask how that plays out mathematically. So how are pure states special cases of mixed states? So let's say, assume we know the state is psi. We know for sure, for some reason, that that's the state. Then how do we write this as a special case of a mixed state, even though it is pure. So we define B1 to be the state psi. And then complete a Hilbert basis. So we obtain Bn n equal 1 to infinity. So the idea is we take the state that we know the system is in psi and call it our first basis vector. And then we cook up a basis vector B2, which is orthogonal to this one. And then the basis vector B3, which is orthogonal to the previous two. And then a B4 that's orthogonal to the previous three. And so in this way, successively, we build up Hilbert bases for the entire Hilbert space. And we have this whole basis over there. Now we have, then we have a mixed state, well, a mixed state type probability distribution, which is very simple. Namely, now we have that rho n, the probability distribution, which is the probability for the system being in the state Bn, is 1 if n equal 1 and 0 else. So in other words, rho n is the Kronecker delta of n and 1. So therefore, the density operator of a pure state can then be written as, well, sum over n, and then we have the rho n and the Bn, that's always the case. But in our case now, because it's a pure state, this is the sum over n, and then it's rho, no, it's not, sorry, the rho is the delta, right? So it is delta n1 Bn, I'm sure you're seeing how this is going. In the whole sum, only one term survives, and it's just B1, which we can also write, because B1 is psi, as psi. So the conclusion is for a pure state, psi, the density operator is rho hat equal to psi. Now let's do a little exercise. If this is true, then we should be able to calculate expectation values for observables when the system is in a pure state using the mixed state formula. Right? Let's try that. So, example, calculate f bar for a pure state using the mixed state equation. So the mixed state equation was, well, mixed state equation, recall, the mixed state equation was that f bar is equal to the trace of the density operator times the observable. So what we have is that the expectation value for our observable is the trace of rho hat f hat, and that's always true for all mixed states. And so it better be true also for pure states, because they are just special cases of a probability distribution that is totally skewed. One vector hogs all of the probability and the others get nothing. So we have this. Now let's see if we can calculate from that what an expression that we can recognize from how we used to calculate expectation values for pure state. All right, so what is this? This is then the trace of, well, what is rho hat here? So now for pure state, the rho hat, well, we have it up here in red. Rho hat is psi, psi, and then we have f hat, right? All right, so let's just keep calculating. This is then, because it's a trace, the sum over the diagonal. So sum over n, and then we choose some arbitrary Hilbert basis, Cn, and then psi, psi, f hat, Cn. So this is an arbitrary Hilbert basis. And notice that this is simply an operator, namely rho hat f hat when spelled out, right? This is just some operator. And then we take the sum of the diagonal elements of this operator in the Cn basis. Since the trace doesn't depend on which basis we calculated in, it was our choice. Now, this expression we can also write with the two factors interchanged. Remember that this is just a complex number, and that too is just a complex number. So therefore, we can exchange their sequence. So we can simply write here psi f hat Cn, and then Cn psi, right? It's the same thing as above. I just switched the two factors in the sum. But now we see that this, together with that, it, sorry about that. The drawing software crashed, so I had to rewrite the last few lines. Okay, so here the point is that we recognize that this combination of the Cn, Cn, together with them being summed over, gives us simply a resolution of the identity. So therefore, this then is psi f hat psi. And remember how what we started with? F bar, right? So F bar is equal to this expression for mixed states, but if rho hat is actually the density operator for a pure state, then this carries through and we simply obtain the usual expression for calculating an expectation value. All right, so all of this is very nicely consistent. We obtain F bar is equal to the old expression. Now I promised that this business with the density matrix would help us with the bookkeeping when it comes to calculating the evolutions that all these various possible states that the system might be in are having, right? If we know what the state of the system is, then we really need to only calculate its time evolution. But if we don't know which state it is in, then we have to calculate all their time evolutions. So let's ask, in the Schrödinger picture, see, the whole question only makes sense in the Schrödinger picture because only the Schrödinger picture do the states evolve in time. So in the Schrödinger picture, how does the density operator evolve? evolve in time. See, it's made out of a weighted sum of projectors into states, and these states are time dependent. Now, the proposition is this. Proposition in the Schrödinger picture, rho hat of t, the time-dependent density operator, evolves according to the von Neumann equation. And the von Neumann equation is IH bar d by dt of rho hat of t is equal to the commutator of the Schrödinger Hamiltonian with our density operator. It will be an exercise for you to prove this. Let me ask, how does it evolve? How does rho hat, oh, this is not easy to read. How does rho hat evolve in the Heisenberg picture? Well, the answer is not at all. Right? Because there it is the observables that evolve in time. Right? Then we simply have that the predictions f bar of t are equal to the trace of, well, rho hat and then f hat of t. The evolution in the Heisenberg picture is here. In the Schrödinger picture, we have f bar is equal to trace of rho hat of t, and in the Schrödinger picture, the observables are frozen in time. So again, as we discussed before for pure states, we can throw the evolution onto the states or onto the observables in the Schrödinger picture or Heisenberg picture respectively, and now the predictions are calculated accordingly. In the Schrödinger picture, it's the density matrix that evolves in time, and in the Heisenberg picture, it's the observables that evolve in time. Now, von Neumann was a mathematician and a physicist, and von Neumann was one of the cleverest of them all in the 20th century. He did more than just develop the von Neumann equation for the time evolution of the density operator. Von Neumann also asked, how well do we know the state? So von Neumann, he asked, how well, or how much ignorance, let's put it this way, how much ignorance do we, oh, I'm so sorry, do we have about the state if rho hat is given, i.e. if the set of probabilities rho n is given. Now clearly, if one of the rho n's is 1 and all the other rho n's are 0, then we have no ignorance. If on the other hand, all the rho n, for example, are, I mean, they're all non-zero and none of them stands out somehow, well, then we have a lot of ignorance about it. And so von Neumann asked, is there a measure of ignorance What is a good measure of ignorance? Let's call it S for rho hat. Requirements. Well, first of all, of course, we want that this measure of ignorance should be 0 if rho hat is pure, right? Because then we have no ignorance. We do know what the state is. So for pure states, the measure of ignorance S should be 0. You may already anticipate where this is going. The measure of ignorance S will, of course, be very closely related to entropy. Entropy being disorder. And knowing a state means no order and no amount of disorder. I know what state it is, right? Okay, but let's do this systematically. So S, for now, we know nothing that it has to do with entropy or not. We just want a measure of the ignorance expressed in our density matrix. And so far we said that, well, whatever that measure S of rho is, it better be 0 for pure states. And then also, the measure of ignorance for a density matrix should always be larger than 0 if rho hat is actually mixed. We don't want to have any negative amounts of ignorance, right? That makes no sense. All right, so you might think, that's good. Could it be that we can now calculate, that we can now invent a measure S of the density matrix? A map S that feeds onto density matrices and outputs positive real numbers in such a way that it outputs 0 if and only if. Let me put here double F. So if rho hat is pure and outputs a positive number if our state is mixed. Yes, we can come up with such maps. The trouble is, there are infinitely many of them. These two requirements are not restrictive enough. There's a huge variety of S's that could obey this. But then von Neumann came along and he said, well, let me not write it as the answer just yet. Von Neumann said, we have to add another condition. And that condition will make our S effectively unique. And that condition is an ingenious condition, but credit shouldn't go completely to von Neumann because actually Shannon came up with it earlier. Anyway, Shannon didn't do quantum mechanics. So von Neumann imported that trick into quantum theory. So von Neumann said now the following. Von Neumann said, as an additional requirement, he said, assume we have two independent systems. Let's call them A and B. Then, together, they form the system AB, system that we may call C. Okay, and well, C is simply the combination of A and B. In this scenario, von Neumann said, well, I mean, this could be like an atom here and an atom over there. We don't know what the status of this atom, we don't know what the status of that atom. Fine. And those atoms are far enough from each other that they don't interact with each other. They're meant to be independent systems, right? And then von Neumann said, well, we can consider those two atoms together as one system. It's the quantum system consisting of two nuclei and so many electrons and so on. It's just a combined thing. Basically, just the two atoms together are also, capable of being viewed as a quantum system. Just like a molecule is a quantum system, even though it consists of many constituents. So von Neumann's ingenious idea was now that our measure of ignorance S should not only obey those simple conditions here, but our measure of ignorance should also be additive under these circumstances. So von Neumann said that whatever that measure is, it should have the property that the measure, when applied to the density matrix of the system C, the combined system of the two atoms, then it should be the same as the sum of the ignorance for the density matrix of the first system and the ignorance of the density contained in the density matrix, the second system. So additivity. Additivity for independent systems. Now, it turns out now with, let's call them 1, 2, 3. So if we call these three conditions here, 1, 2, 3, S of rho is essentially determined. There's some caveats, but we won't go into those in detail now. I will have much more to say about it later. So with these conditions, this S is essentially determined. And what is the answer? The answer to the question of von Neumann, how do we quantify how much ignorance we have about which state the system is in? The answer is that we should use as the measure this S, and it's not completely unique. There are a family of these S's labeled by a positive number A. And they work in the following way. So we take this ignorance function, the ignorance function will take as its input a density matrix and will output a real number. And what's going to be the real number? Well, it's calculated as follows. It's the negative of the trace of the density matrix times the logarithm to base A of the density matrix. And then here, A larger 0 is an arbitrary constant. It will be very important later on, but for now, it's just, it will have an important interpretation later on. But for now, it's an arbitrary constant, this A. Now, this looks a little dangerous here, right? We are taking the logarithm of an operator. What is that supposed to mean? Well, first of all, the claim is so that this is the answer, that is to say that this obeys 1, 2, and 3, all those three requirements. And you may wonder, how come that we have a logarithm in here? how do these innocent looking conditions here have as their solution something that has a logarithm? Well, the reason is fundamentally this, and I write much more about this in the lecture notes. In the lecture notes, I go into more detail in case you're interested in these subtle details there. So the reason why a logarithm arises here is this. When you have two systems, and each one has a probability distribution, and then you consider the combined system, then the combined system also has a probability distribution. Namely, the individual probability distributions, let's say for the first system, system A, is of the following form. It gives us for every state that system A could be in, and in one of this Hilbert basis, it gives us a probability for the system of the states to be in that state. The second probability distribution gives us a probability for, the second system to be in any one of its states. The probability distribution of the combined system gives us a probability for the first system to be in this state and the second system to be in that state. It gives us a probability for the first system to be in that other state and this second system to be in that other state, and so on. And how do you obtain the probability distribution for the combined system? Well, by multiplying the probability distributions of the individual ones, right? The probability that you get this state here and that state there is the probability for this state multiplied with the probability for that state. Long story made short, when you have two independent systems, the probabilities multiply in order to give you the probabilities for the big system. But the requirement for S is that it is additive, not multiplicative. Von Neumann insisted that the ignorance, the amount of ignorance that I have about the first system and the amount of ignorance that I have about the second system should be added together to tell me how much ignorance I have in total about the total system. Therefore, the probabilities multiply, but the ignorance measure should be additive. And that job can only be done by the logarithm, right? Because it turns products into sums. That's fundamentally the reason why this measure of ignorance S contains a logarithm. Okay, so for now, let me just claim that this is the answer in the lecture notes, and partially I'm asking you to prove these things. This is proven that this is actually solving our three conditions here. But first, before we go into the proof of this, let's see, how do we actually calculate this? Given that we have to take a logarithm of an operator, apparently. Well, it's not so hard. How to calculate? But remember that whenever we have a function of an operator, it's a good idea to go into the eigenbasis of that operator, if it has an eigenbasis. Now, our density operators are all self-adjoint, therefore they do have eigenbases. And so use eigenbases. Now, when we do that, then we obtain that SA of rho hat is equal to minus sum over n. And then we write here the trace, and we choose for the trace to use the eigenbasis of our rho hat operator. So if the eigenbasis is called Bn, then we have here Bn rho hat log A of rho hat and Bn, right? So we are summing up the diagonal elements of this operator in the eigenbasis of rho hat. Now, when we apply rho hat onto one of its eigenvectors, we just get the eigenvalue. Let us recall what's going on here. So, recall. We have that when rho hat acts on Bn, then this is rho n Bn. If rho hat to the rth power acts on Bn, then we get rho n to the rth power of Bn, simply by applying this equation multiple times. And more generally, we have that when we have a function of rho hat, which could be just rho hat to the rth power, it could be the exponentiation of it, or any of these, and we apply that to the Bn, then we obtain that function of the eigenvalue rho n acting on Bn. To fully justify that, we would have to go into the analysis of the logarithm, express it in a way such this makes sense. We have to have an expansion of the logarithm for this. But this can be done, and this is not a course about functional analysis. All right, so we have this, and from that then we obtain that, coming back to the equation that we're working with here, that this is minus the sum over, and then we have here that the rho hat becomes just a rho n, and this log base a of rho hat becomes just a rho n as well. So then that becomes sum over, well, principle we have here still the Bn. And then we have the rho n, and then the log base a rho n Bn. But this is just numbers. And so therefore this is minus sum over n rho n log base a of rho n. All right, so what we have, just to summarize this, is that SA of rho hat is equal to this. Now, if we write the von Neumann expression for the ignorance in this way, then we see that it is basis independent, which is nice to know, but it's hard to see how to evaluate it. If, on the other hand, we do this calculation, then we find that this expression takes this particular form. And at this point, we notice, or von Neumann noticed first, that this is the form of a Shannon entropy for a probability distribution rho n. Probability distribution is, of course, simply a collection of numbers from 0 to 1, which sum up to 1. So in other words, this is a Shannon entropy. This is a Shannon entropy. Actually, because it is arising in quantum mechanics, and because von Neumann first discovered it here, this is actually called the von Neumann entropy. So in other words, the von Neumann entropy is the special case of a Shannon entropy arising in quantum mechanics. You may wonder, how come it is exactly a Shannon entropy? Aren't we doing quantum mechanics? Shouldn't there be some sort of quantum generalization of the Shannon entropy? No, not really, because You see, Shannon entropy is truly something classical. Shannon has not worked on quantum mechanics as far as I know. Shannon entropy is about classical probability distributions and measuring how much ignorance is expressed in a classical probability distribution. And von Neumann found this occurring in quantum mechanics, but there's no quantumness in it because it is not describing nature. It is describing our ignorance about nature. And our ignorance about nature, our assignment of probabilities to the system being in this state or that state or that state, that's a classical thing. So the von Neumann entropy is the classical ignorance, the classical measure of ignorance, of how much we know about what state the system is in. Now let's do a bit of a check here. Remember, this expression here for the von Neumann entropy is supposed to obey our three conditions above. So let's check. Well, there was condition 1. So assume pure state. Well, i.e., we have that rho n is equal to the delta of n and then some n naught, right? Because we know that the system is in some state b n naught, b5 or whatever. But then the von Neumann entropy of our state rho is what? Well, then it is minus sum over all n, and then it's the rho n, and then the log base a of rho n. Now, this is equal to 0 for all n that are not equal to n naught, right? Because this is 1 if n is n naught, otherwise it's 0. How about this one, this rho n? Now, this rho n is 1 when n is equal to n naught. So, but a to what power is 1? Well, 0, right? So this is equal to 0 if, so this entire log is equal to 0 if n is equal to n naught. So therefore, this whole thing is equal to 0 for all n. Sorry, I shouldn't go all the way here. I only wanted to go that far, right? So for all n, and so therefore this is equal to 0 for pure state. For pure rho hat, as it should be. Now, if you have paid very careful attention, you may have noticed that I glanced over a little detail here, which is that when n is not equal to n naught, then the argument, the log here, is 0. But the log to whatever basis of 0 is minus infinity. So what we have competing here is a 0 coming from the prefactor multiplied with a minus infinity arising over here. What's winning? And I just claimed that it's the 0 that's winning. It's really 0. Now, one can derive that more carefully. Namely, you can start with a probability distribution where you don't have this Kronecker delta just yet, but you have one peak here at n naught, and then the others still have some probability, but you make that the probability for the other states go to 0, while piling on the probability on that one state b n naught. And then if you carefully take that limit, you will find that yes, it is as we said here, and you get a 0. And the reason is ultimately that the log is very slow. This goes to 0 before that goes to 0. And this goes to 0 faster than the log goes to -infinity. That's why in the limit taking, this is winning. All right, so this is for pure states. Now, secondly, for mixed states, rho hat mixed. Our requirement for mixed states was, second requirement was that the von Neumann entropy, or whatever the measure would be called, well, it is minus sum over n, and then we have the rho n and the log base a rho n. And we wanted this to be larger or equal to 0. But is it? It looks like it might not be because there's a minus sign. The answer is yes, it's always positive. And the reason is that the rho are between 0 and 1. And since the arguments of the log are between 0 and 1, the log always comes out negative. So this is always negative, always canceling that negative sign here, and therefore we always have that this is indeed positive. So that condition is met as well. Okay, and then there was still the case of 3, which is the additivity for independent systems. Or more generally, the additivity for independent probability distributions, because it doesn't have to be about quantum systems. It's simply about 2 independent probability distributions. And this I leave to you as an exercise. All right. This leaves open the question, what does the parameter A mean in this? Couldn't they just fix that as well? Add a fourth condition and then get rid of the A and it's all fixed? So let's see. What does the A mean? What does A mean in the von Neumann entropy? But to understand that, let's go back to Shannon. Shannon showed, by the way, in case you don't know, Claude Shannon is sort of the Einstein of information theory. In the 1940s, Shannon developed information theory. He wrote a book called The Mathematical Theory of Communication, and it laid the foundation to information theory and therefore to our information age and computer science and all of that. This is a little booklet which you can buy, but it's also freely available on the internet. And it's widely considered to have been one of the most influential books of the 20th century. In fact, there is an edition of the book by Claude Shannon, and the other author's name is Weaver, Shannon and Weaver. Let me just write that here. Shannon and Weaver. That book is very nice, very easy to read, and Shannon was a genius. So if you have some spare time and you're interested in the foundations of information theory, definitely look up the book by Shannon and Weaver. Okay, so Shannon showed that the Shannon entropy, in quantum mechanics called the von Neumann entropy, but it's really the Shannon entropy, of a probability distribution, or one wiggle too many, of a probability distribution of probabilities rho n, where it is defined as we said earlier, sum over n, and then rho n log a rho n, is equal to, and this is now the answer to what the A is equal to, and I will try to write this in a very legible way because it's so important. It's the number of questions with A possible outcomes outcomes each that are needed to remove the ignorance. See, now that's a beautiful answer here. For example, let's say a coin is hidden under one of 4 cups. Then how many questions with 4 possible outcomes do we need to ask to remove the ignorance about where the coin is? Well, one question with 4 possible outcomes that I can ask is the coin under the cup 1, 2, 3, or 4? Well, then I get the answer and then I know where it is. One question with 4 possible outcomes suffices to remove my ignorance. But imagine I'm restricted to asking questions with 2 possible outcomes. Well, then I will need to ask 2 questions, right? So, for example, the first question could be, is the coin in cups 1 or 2 or not? And then I get the answer. For example, it's not. And there was only one of 2 possible answers, right? It either is it is under the first 2 cups or it's not. All right, and then the second question with 2 possible outcomes I can use to distinguish between the 2 remaining cups, and so on. So this is what is meant by questions with a possible number of possible outcomes. So the definition now is this. A equal to means S2 of rho hat is the number of binary questions needed and we say i.e. we measure ignorance, or when you get your answer, then you don't call it ignorance, then you call it information. We measure ignorance in bits, what is called bits. This is the origin of the word a bit of information. And if, for example, we choose a equal to 3, then S3 of rho hat is a number of, well, let me just say, I mean, you know how this goes, right? Number of questions with 3 possible outcomes, and then we measure in trits. Measure in trits. Another popular choice, I mean, this is the choice of computer science. And then sometimes you may want to choose the base 10, perhaps. But if you choose A equal to E, then we have SE of rho hat, which means that you're using the natural logarithm, so that you don't even write the base anymore. And in that case, the unit of information or ignorance is called, we measure in nats. So physicists measure information in nats. Now, how are they related? Is this a completely different information theory if we choose A equal to, then, for example, we choose A equal to E? Are there going to be any significant differences in this? Well, not really. So differences for different A. Not really. Namely, recall we have that SA is equal to minus sum over n and then rho n log A rho n. And then remember that the log A of some number rho is equal to the ratio of the log B of rho divided by the log B of A for any A, B rho larger 0. And therefore, we can now relate the von Neumann entropy or the Shannon entropy for different values of A, let's say A and B. Namely, therefore, we have that the von Neumann entropy for informational unit B rho is equal to the von Neumann entropy to the base A of rho times log of A to the base of B. And this is just a real number. So therefore, the von Neumann entropies or the Shannon entropies to different bases only differ by a constant. It's constant because it's independent of rho hat. So therefore, it's completely independent of the physics of it. Therefore, it doesn't really matter at all when we measure whether we measure our ignorance in bits or trits or nats or other units. It's just an overall prefactor. It is as if we measure distances in kilometers or in miles. All right. Now, let me tell you, just to close this, a little thing that goes back to Shannon. Remember that von Neumann's big insight was that if we want to quantify the amount of ignorance we have about the state in which our system is in, then one of the conditions should be that this ignorance is additive when we have two systems. The ignorance, the amount of ignorance about the state of one system plus the amount of ignorance about the state in the other system, measured, for example, in the amount of bits of information that we are missing here, should be additive, so that the ignorance that we have about the total system should be just the sum of the two, if the two systems are truly independent. And this idea, I said, goes back to Shannon. But Shannon didn't know about quantum systems or ignorance about quantum states. Well, maybe he knew about it, but he didn't work on quantum mechanics. So how was Shannon led to this same argument in a different context? Well, his context was information theory. He asked, how much information do I receive when I have a source of information that sends me symbols? Let's say that sends me, I don't know, one symbol per second. See, in the 1940s, communication was slow. So let's just say you receive one symbol per second. It wasn't that slow. Anyway, so let's say you have a communication channel with one symbol per second. Let's say you are a newspaper editor and you have a correspondent in China, and you have a correspondent in India, and you have a correspondent in France. And they each wire information to you. So they send you symbols. And let's say you receive symbols from China, symbols from India, symbols from France. And then you can ask, how much information am I getting per symbol from those messages? And Shannon noticed that the symbols that came from China come from a huge alphabet. And there is a certain probability distribution. Some symbols will be sent much more frequently than other symbols. Then the Indian alphabet has only a few hundred symbols, like 250 symbols or so. It's still a pretty large alphabet, but not as big as the Chinese. And they have a different probability distribution, those letters. And then the symbols from France, yeah, there are not that many in the alphabet, in the French alphabet. But again, they have a probability distribution. And Shannon asked, well, okay, so how can we tell how much information we get per symbol from the one language, from the other language, from the other language? And his idea was to say, I have these probability distributions there. I want to find some function S that quantifies the amount of information that I get, or that removes my ignorance about what happened in India, or what happened in China, what happened in France. And then he stumbled upon this idea that whatever that measure of the amount of information should be, it better should be additive, because the amount of information you get in the messages from China is independent of the information that you get from, another country. And if you get the information from multiple countries simultaneously, then it's like having a combined quantum system with subsystems, right? You just have a combined source of information that consists of sub-sources. And he insisted on the additivity, in spite of the fact that the probabilities for the letters in the alphabet multiply when you look at the joint arrival of messages from all the countries. And from that, he deduced that information ought to be measured by the Shannon entropy formula, this thing that contains the log. And that has proven to be invaluable, of course, and it was the foundation to classical information theory, and now we extend this to quantum information theory. But as far as the lecture today was concerned, this was a classical information theory overhead. It was a classical information theory analysis of classical ignorance of what quantum state the system is in. All right, so this is as far as we got today. See you then.